Okay, let me just finish where I was at with this right here. Here, this discussion up there. I was going through VHDL, and probably I'm going to jump. I don't know where I finished on these slides right there, but basically every VHDL file or piece of logic or hardware, however you call it, has three basic things that are part of our VHDL code. The top part here is the library declarations. VHDL has been around since the 1980s. There's IEEE basically handles all the libraries available for VHDL. So normally you just tell the code to use the IEEE library. Now you may have to add some other libraries to it that's specific to particular hardware there or particular things you're going to do, but you just simply have your library declarations. It's very easily done. Then you define the entity and then the architecture. The entity, and I thought, okay, and why are we moving so slow today? Right there. Okay. The entity basically is the black box. Right there. And you tell it what the inputs and outputs are of the black box. The architecture, architecture, ARCH, is what's defining the functionality inside the black box, right there. So when we do a VHDL, we have two parts of it. One is the entity, and that's just telling it what it looks like. And the reason we do the entity is because we quite often will want to connect this to other devices using there. One of the things about VHDL, if you remember, we did the one project a while back with the adder, where we had the full adder, the half adder, and we could connect those boxes together. There. So if you look at that there, we created a symbol for something, and then we created another symbol, and we interconnected those, right? That there. Well, the entity tells it how to make that symbol. So if we want to interconnect it to other things using the block schematic editor, because we can do a VHDL subdesign and stick it within another circuit, right there. So before we did a schematic and then we stuck that in and had multiples, we could do the same thing with VHDL. We can design, and this next discussion actually gets into that there. But we can design the libraries list of all the libraries we used. That's fairly easy. Specifies the I/O pins of the circuit is what the entity does. And then the architecture is the heart of any VHDL description. Now, if you're working with HDL or Verilog, they have similar types of discussions out there, because all three of these are hierarchical design description languages. And since they all three do the same thing, they look very similar to each other. That's there. So I look at it as when you learn to drive a Proton Wira. 5 years later, you got your real job. You went out and bought a Mazda MX-5 right there. I mean, you got a good first job, right? I mean, they're both cars. They both drive the same way. But the gear shift is over here on this car, it's over here on this car, the light switches that there. The same thing with design languages. They all do the same thing. My wife has a Purdue MyV, I have an Ulsa. They're both cars. Now, things get really more interesting is that in January, for example, I'm going to go back and visit my son and grandchildren and all that, and my son bought I don't know what car, he bought a Nissan Altima or something that he says that I can drive when I go back there. Then everything changes because the steering wheel moves to the opposite side of the car. And then I got to drive on the other side of the road. And then the speedometer is now in miles per hour instead of kilometers per hour. So I have a much bigger change. I'm still driving a car. That's there. That's the same concept with computer programming. You learn C programming, your first course. Later on, you're going to take a course in microprocessors, and you're going to be using assembly language programming. You're still writing programs. Now, assembly language programming is a little different because you're getting down to the hardware level, so I shouldn't use that as an example. Let's say, something's in my ear, but let's say, for example, the next language comes up, and you're going to do a project, and you have to use Python. You know, Python is a very popular programming language used for embedded or small boards like the Raspberry Pi uses Python for programming. Or you're going to write web software and you're going to use a form of HTML. You're still writing computer programs. So when we look at VHDL code, and it's got three basic fundamental sections: the libraries, which is just a list of libraries, it's not really part of the code, the entity, and the architecture. All these languages have similar types of that there. So we're looking at our example right there. Might as well use the same example that we did there. We have a full adder. A full adder contains our schematic. What it looks like on the outside has three inputs. Now this particular author didn't call it A, B, and he called it A, B, and C in. That's perfectly fine. Notice that my entity right up here, only lists what I see on the output right there. So as I look at the block diagram, the entity just simply repeats what's on the block diagram. That's there. The architecture tells me what's inside of that there. Now, if you look at the code here, we use simply the logic circuit right there. This says that S is equal to A XOR B XOR Cn right there. So that particular circuit right there. Now you could put, for example, a parentheses right here if you want to specify a little bit different. The compiler can figure this one out. Is that we're trying to do XOR 3 different there. If you look at the XOR, the sum out or the full adder, you would see a circuit that looks something like that. And then this is the logic for the carry out. Now there's other ways of doing that there. This is just using that there. But this just simply says what's inside this box right there. So this is another way of doing it. This just shows the simulation of doing that. That's not using that there. So this is a full program or full description right there. So I'm not going to get into much details on that there. Our library declarations, normally we use just library IEEE semicolon right there. You can use IEEE standard logic 1164.all right there. So typically you just simply say use IEEE. Normally this one here is the only one I ever put in the beginning right there. What library you use is completely up to the right there. Normally you just look at the documentation or the example for the compiler you're using in the hardware, and they're going to tell you use the latest IEEE library right there. So IEEE specifies multi-level. It goes through all that there. We have some logic types where we can have 0, 1, high impedance, weak unknown. Now these here that are highlighted right here, these are the ones normally used for synthesizable VHDL. The other ones where it shows U, X, W, L, and H, those are typically used for simulation purposes right there. And then we also have a don't care. Again, we set the entity. We can set up ports at there, and these can go for outside. I'm just kind of skipping through some of these right here. This just simply says an AND gate right there is a port right there, entity right there again. Architecture denotes in the code right here. So this is just going into a little bit more detail. This just simply says that here the architecture of an AND gate is A NAND B right there. So far the VHDL doesn't do much for us at there, because all we're doing is just sticking in logic that there. Now, as we go through that there, I want to get some other things as we look at there. One of the things I should point out is that a lot of people will look at VHDL as a computer programming language. It is not, because it allows us to have things happen concurrently right there. We can have concurrent blocks right there. So we've got the standard arithmetic logic functions right there. Here's an example of a mux right here. This is a poor example of a mux right there. This is a better example of a mux right there. This is using a mux right here where we write all the logic functions right there. That's the way we would do a mux if we were to draw the schematic right there. Again, I download these slides, and for some reason they're bulleted instead of the right format, but this is library, IEEE, use IEEE, standard logic 1164 all. This is the entity for the mux right there. That just simply says it's got A, B, C, D. We got two select lines, and we have a standard output Y right there. So this is a mux that's when S0 and S1 is 0, 0, it's going to select A, it's going to select B, C, or D right there, depending on what input that's there. That looks ugly. Now, VHDL, this is where it looks a little bit better, is now we can say right here, Y is equal to A when select is equal to 0, 0. Else, B when select is equal to 0, 1. Else, C when select is equal to 0, 1, 0. Or D is the last one right there. Don't ask me what the 17 is that there. That's that there. So, again, you look at this, this looks a little bit more like what you would do in C, right? Which one's easier to understand or to write? The second one, obviously. We can simply say, we look at 0, 1. Now, again, what we've got here is we've got here, let me point out a couple other things. Here's our select line right here. Notice that I tell it that it's a standard logic vector, 1 down to 0. Down to 0 means that its most significant bit's 1, least significant bit is 0, and those are labeled here as S1, S2. Therefore, I can use that as a vector here, right there. So I can write a mux, designing mux very, very simply by just using essentially a when select statement right there. Right there. So this is actually all one statement. Should note if you code this, the semicolon goes at the end of everything. Right there. So it's A receives a value, Y receives the value of A when select is equal to 0, 0. Else, B when select is equal to 0, 1. Else, C when select is equal to 1, 0. Else, D, end of statement. The semicolon is the end of the statement. This actually can be written as one long statement right there. And if you look at the syntax he used, he didn't break it up. Normally you would write this as Y A when and right there when select is equal to, okay, I want to make sure I get the syntax right, when select equals else B when else C when else D semicolon. In other words, you would have one line for each right there. So that's a little bit more readable. You know, again, right there. So, and again, you would just begin each one of these and you would indent these where the A, B, C are all in line with each other. The wins are all in line and the right there. So, but basically this is the basic concept of VHDL right there. Now, we have some other things, alternative, right there. begin, that's there, begin when select else B when, and I'm not sure what this is right there, begin A when select is equal, okay, all he's changed here is he's used the numbers instead of the, decimal numbers instead of equal to 0, 0, which is a little bit more readable then. So, but you can see the flexibility we're starting to look at right there. We can also do tri-state buffers. That's there. Output is equal to input when enable is equal to 0, else others, it's when everything goes to Z right there. So we can also set up tri-state buffers at there. Now, something that VHDL allows is what we call behavioral code or processes. And that's where we do a finite state machine. That's there. I'm probably not going to go very deep because I got another subject that I want to completely change gears that goes back to like the 5th week of the semester that I need to cover before I forget to cover because it's on the final, or one version of the final. So I need to come back and cover a particular topic right there. But let me talk about sequential statements. Is that the term, if you use a process, that means everything within that process is done in a sequential fashion like a computer program, and it is only done when something occurs in what they call the sensitivity list. We'll see some examples. I don't know if these slides, I have not looked at these as carefully. They should have the examples I'm looking for right there. We can put if statements. We can put a case statement. If, case. So we can do an if then else statement right there. We can do if then else's. We can do a case statement, which is very handy for finite state machines because we can have a case that lists what state we're in and then go through and figure out which state to go to next. Right there. We can have a loop statement where we do something a certain number of times, so if we want to have a timer, for example. We have next statements. We can exit, we can wait. Now the wait we don't necessarily use very often. Not in synthesizable. We can have functions and procedures, which we're not going to get into in this class, where we can actually make things look more like code. A process is sequential, characterized by the presence of if and else sensitivity lists, except for when the wait is used, must be installed in the main code and executed every time the signal in the sensitivity list changes. Or the signal related to wait. Again, ignore this discussion of wait. Wait is not part of synthesizable VHDL. That's there. So what this essentially says is that whenever we have a process, we have a list of signals that they're, like, for example, one of the signals may be clock. So if the clock doesn't change, everything in that process is ignored. It only looks at a change of a clock. Reset could be another one, or clear not. So this process has these sensitivity lists right there. So our syntax is basically straightforward. It's within the architecture. A process is only within architecture. It's not within the entity. The entity, remember, is just a black box. There's anything else. All the entity lists is the name of the black box and what you can see from the outside, the inputs and the outputs. That's the only thing in the entity. Everything else is in the architecture. So when you look at VHDL, Verilog, or AHDL, you're going to have the entity or whatever it's called, and then the architecture. So within an architecture, we would start a process right there. It has some variables. We can have variables within our process. Those variables are only seen within the process. They're not seen outside the circuit. We can't print them out. We can't look at them. They're just internal variables that we can use internally. They can have a range. They can be vectors. They can be single bits. That's there. They can be strings, which is right there. And then we have sequential code. And then we have the end of the process, which may or may not contain the label. I always include the label, because the label basically just simply tells you what the name of the process is up there. If you notice that there's no label at the top, it's just process. So the system, and this is blue so you don't see it. Let me go to a different color. Right there. See, when it sees this word process right here, sees this process, and I think I got a bad battery. I just replaced it not too long ago, but it keeps. All right. When it sees this here, it's looking for the next end statement. So these have to line up. You cannot have overlapping processes. You know, in C, you could not have a loop here and then another loop here, right? You can have a loop within a loop, but you could not have overlapping loops. Same thing with processes, right there. This is not a course in VHDL. We're only seeing about a couple lectures on it, so we're not going to get into multiple processes. You can have, though, within a VHDL design, multiple processes, and most VHDL designs do have multiple processes. You can have multiple processes, and you can have concurrent code within the same design. See, this is where people get very, very lost and confused with VHDL, is that if I write code in C, it does one thing and one thing only at a time, right? I calls an interrupt, it processes the interrupt, and it goes back to the main set of code. Right there. When I'm writing VHDL, I'm designing hardware. I can have 3 different processes operating at the same time, along with combinational logic, all occurring simultaneously. Why? Because I just add more flip-flops and more gates wherever I need it. Right there. A microprocessor has one accumulator, one set of registers, one data bus, one address bus. It can only do one thing at a time. It goes out, it reads the instruction. Right there. Now, I lied to you there. That is a typical standard single-core processor I'm talking about. When we look at some of the multi-core processors, some of those are doing multiple tasks simultaneously. Right there. But we're going to assume that those don't exist for sake of discussion. Most programmers do not think in terms of multiple threads running simultaneously. Right there. So this is the syntax. So we have an example here. Again, the example is poorly formatted, but if we look at the example here, this is our entity, excuse me. This is our entity right here. This is our library definitions right there. This is our D flip-flop right here. This is the architecture behavior of D flip-flop. Now, this name has to match this name, has to match those names. DFF has to be the same all the way through. That tells me what the name of this block is, DFF. So DFF is a black box. It's got 3 inputs, D, clock, and reset. It has 1 output, Q, in this case, right there. So we list our ports there. Our architecture, behavior, D flip-flop, begin. This is a process. We want things to happen sequentially, right there. Our sensitivity list is clock and reset. Nothing happens unless the clock changes, right there. So, process, begin, reset and clock. If reset is 1, then Q goes to 0. So this is an active high reset. That's there. If I want this to be an active low reset, I would probably call it reset not or reset n, and say if reset is equal to 0, then 0 goes to Q, right there. So this just does the reset. And it says else if clock event, something occurs on the clock, and clock is equal to 1, right there. This is telling me that on the leading edge of the clock, I want whatever's on D to move to Q, right there. And if, right there. So here's my if-then statement right there. That handles my D flip-flop there. End of my process, end of my behavior. So this is a D flip-flop designed in VHDL. Right there. Now you should notice that when we designed this with NOR gates and NAND gates, it was very difficult to understand what was going on, right? You had to kind of go through the trace. Here we can actually follow the logic and see what's happening. It's a much better way of designing that there. So I think you can understand why I prefer this method of working. Unfortunately, this course just touches on it a little bit. That there. Here's an alternative to it. This uses the wait on, reset, and clock. If reset is equal to 1, else if clock, that there. I have never used this technique of doing the wait on. The wait on is not very rarely used. But this is basically the same thing as putting in the sensitivity list. Here, the sensitivity list does the same thing as the wait on, right there. The case statement is a very powerful tool, and I'll come back to the case statement later on. Is that typically I use the case statement a lot for. You're dozing off. What's going on here? Is it 12 o'clock? Did you guys eat late breakfast or something? What? That there? Or there? You know, the rule is if I got to stay awake, you got to stay awake. This is, and trust me, I just went through some of the same discussion last hour with another class. So if you're bored with the repetition, imagine how I am after teaching this for 30 years. That's there. So regardless, the case statement is a very, very powerful tool intended exclusively for sequential code. This is case identifier. So we can use, for example, case state machine, which is a variable name that happens to have a series of states listed. It could be my list state. So case identifier is when value, when S0. Then I don't necessarily have to have this when here. Value is assignments. That there. I can have other code there. I can put an if statement there. I can make that there. So if input is equal to 1, my next state is this. My outputs are this. So I can do an entire right there case, but this is a case control. When control is equal to 0, 0, A goes to X, B goes to Y. Now, later on, you're going to be taking assembly language in a microprocessor course, and you'll see this same type of thing where you'll see something that says move A, B right there. It moves this direction, and this does the same thing. We're moving from right to left. So X is now going to contain A, B is going to, as it turns out, this little arrow helps you out. One of the problems that people have with VHDL is they don't know when to put the arrow in and when not to put the arrow in. And I'll be honest, I don't remember half the time either. And I let the compiler tell me when to do that there. But what this is saying is that when control is equal to 0, 0, X is going to be equal to A, B is going to be there. When control is 0, 1, X is going to get B and Y is going to get C. Now we're assuming for this argument is that X, A, and B are all a bit vector 3.0. In other words, it's a 4-bit vector is what it is right there. And the reason I make that assumption is from here and here, right there. So it can be 16 bits, it can be 8 bits, it can be 4 bits. It doesn't really matter. But all we're saying is when control is 2 bits, we can tell that. When control is 0, 0, X gets the value of A, which is a 4-bit number. Y gets the value of B, which is a 4-bit number. If 0, 1, X gets B, Y gets C. If it's 1, 1 or 1, 0, you know, the other two combinations, and that's the others, because there's 4 possible combinations, 0, 0, 0, 1, 1, 0, 1, 1. We've defined these two. These two are our others right here. They're defined here. They're that others category. So in that case, X gets zeros and Y gets a high impedance output. It goes as Z. So that there. So this is our case when particular state. This is one example that there. So again, here's another right here when right here. So our process list says that when clock and reset change begin case, when reset is 1, we just set Q is equal to 0, right? So we're doing a reset. When 0, if clock event and clock is equal to 1, then Q gets D. So again, we're looking here at, this is a very simple when 0, 1, but you can see that I'm sticking in here an if then else there, so it doesn't have to be a simple. So I could very easily, and we'll come back to a more complex finite state machine that we can do using VHDL, and we can do a very complex finite state machine using VHDL. I can pull up one that's like 2 or 3 pages and go through it, and you can see how simple it is to understand what's going on right there. So when others that there, and this when others actually sounds a little crazy. You normally wouldn't need that, but that there, because you've already handled the 2 cases of reset 1 and 0, but you normally stick the when others there just because VHDL likes it. The code ends up being a little simpler right there. So, all right. I'm going to stop at this point right there, and we're going to come back to this a little bit later. I want to spend a few minutes talking right there. That's my last class. I want to just shut that there. At the end of class, hopefully I can get to the internet and I can upload that stuff there. Okay. Now let me kind of talk a little bit about a subject we talked about much earlier in the semester, and I hate to go back to it, but if I didn't cover it right the first time and it's on the final exam, I'm going to feel horrible about it. So, and I wrote 2 versions of the final exam, multiple questions, and it is on one of the versions of the final exam I wrote. So I want to make sure that I cover the material well. I don't guarantee you're going to see this problem, but there's probably about a 50 chance you might see it that there. So I want to cover that. And that's going back to this discussion of, we've been using what's called sum of products. And this is going back to our early one, where it's our A, B, C naught plus A, B, C plus B, A naught, B, C naught. Something like that is equal to X right there, right? That's a standard sum of products right there. And the way we would design that, that would be 3 AND gates right there. And let me just say that when you take the final exam and I tell you to do a design, don't draw all the wires. It's okay to just put A, B, let's get them right here. A, B, C naught, like that there. You don't have to connect it. Come down here, A, B, C, A naught, B, C naught. Don't show all the interconnections and all the wires. That just gets really messy and it's too easy to make a mistake. Plus, it makes my life too hard to grade. That there. So I'm being selfish when I say just do it this way, right there. It's much simpler, it's much cleaner, and it's easier. we know that A comes in, it drops a rail down, it's connected across there. But just keep your life simple and just do A, B, C as your inputs here, and not show the inputs back here and how they're connected. Right there. I just want to make that clear. And then this would go into an OR gate right there. And this is X out. Now, if I put a bubble here, and a bubble here, a bubble here, a bubble here, and a bubble here, and a bubble here, I have not changed the circuit right there. I place an inverter here, and then I put another inverter on the input there. I have not changed that. Now, as it turns out, this circuit here, right here, and let's just look at this here, A, B, C, and this is X out right there. That X is equal to A naught plus B naught plus C naught, right? Well, that happens to be equal to, right there, A, B, C, right? Knotted, right there. That's De Morgan's theorem, right? So if I have a gate that looks like this is the equivalent of a NAND gate, right there. This is another way of drawing a NAND gate, right there. Right there. That's another way of drawing a NAND gate. So I can take any sum of products circuit, and I can implement it only with NAND gates. Up there. Now, I know I covered that part before. I mentioned that before. But what I'm going to mention here in a few minutes, I may or may not have mentioned before. Up there. Up there. So that's the case there. Now, any circuit that I am going to implement as a sum of products right there, if I have a test question that I say implement the following truth table using nothing but NAND gates, what you need to do is you need to solve the problem with sum of products notation and just show it just like that right there. Right there. That's fine. However, what I did not probably cover very well is what if I be really nasty and say, here's a truth table, solve it for using nothing but NOR gates. I did not go through that example. That's there. And that's what I want to spend the next 10 minutes, 15 minutes going through how we would do a circuit using nothing but NOR gates right there. So let's go through, and let's just say we have an arbitrary function A, B, C. And we'll throw D in here just to make things interesting. X. I probably should have just stuck with A, B, C, but we'll just go through it. Supposed to be able to there. And I'm going to do, last time I did this, I came up with the ugliest Karnoff map on the planet. I'm just going to do it relatively straightforward here. And hopefully it's not ugly. All right. Why is this not working? No, it doesn't want to let me zoom out or up there, so we'll just have to live with what we've got here. So I'm just going to go ahead and put the numbers here: 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And I'm going to put my Karnoff map here. This is A not B, B not, A not B, A B, A B not, C not, D not, C not D, C D, C D not, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. All right. Now, I'm going to go through here and hopefully I get this right here. 0, 1, 2 is 0, 3 is a 1, 4 is a 1, 5 is a 0, 6 is a 1, 7 is a 1, 8, 0, 9, 1, 10, 1, 11, 0, 12, 1, 13, 0, 1, 1. Okay. All right. Copy. All right. Now, here's what there. Now, if my question is, that doesn't sound good. If my question is, find this, simplify this circuit, you can do what you've been doing. Go through and circle all the ones. Right here. So, in other words, I would have a group of ones here, a group of ones here, and it looks like a pair of ones here and a pair of ones here, right there. Does anybody see? Oh, and I missed one here. This one would be across there. And actually, got there. But you circle all the ones. Now, if my question comes in, and this is where what's different, if I say find the simplest NAND gate circuit, right there, you would do exactly what we've been doing. However, if I say find the simplest NOR gate solution, and this is what I don't think I went through last time very well. If I did, I may have missed it. If I say NOR gate, that means it needs to be a product of sums, right? It needs to be in this product of sums. It needs to be in the configuration that looks like this, right? And that configuration looks like this: A plus B naught plus C plus D naught, ended with A naught plus B naught, in that type of configuration, sum of products, or a product of sums right there. The way that you do that is you don't read the ones. We want to find out what the function is not. So the process requires that we read the zeros out. So going back to this right here, we circle our zeros right here. So when we look at the zeros, we've got 2 zeros here, right there. We've got 2 zeros here, and we've got 2 zeros here, and 1 zero here. So we read, now you got to follow me, we read the zeros out. So if it's going to be a NOR, we have to read the zeros right there. So we read our zeros. So our first pair, let's do the first one. That looks like it's B naught, C naught, D naught right there. And we write it down just like we did before. Or, that's this pair here. This pair here, what changes from there to there is the C, so that's A naught, B naught, D naught right there. That's this pair from here to here. This pair here is B, C naught, D, right? Then I'm left with just this one here, which is A, B naught, C naught, D, right? Okay, now okay, copy. Okay, so we've got this expression right here. This is what we read out the zeros, so this is what X is not. So number one is read the zeros. Right there. So 2X naught is equal to whatever we read out. So X is equal to whatever we read out knotted. So X is now equal to B, C, D, not, or A, B, D, not, plus B, not, D, plus A, B naught, C naught, D, all knotted right there. So now we start applying De Morgan's theorem. That is equal to B naught, C naught, D naught, not, A naught, B naught, D naught, not, B, C naught, D naught, A, B naught, C naught, D, all knotted. Right there. I think some of you are seeing where I'm going with this right here. And I don't think I covered this last time. I did cover it? No, I did not. And if this showed up on the final exam, you would have had problems with it, right? That's why I wanted to come back and spend a few minutes making sure, and I may do that with other problems. You know, it's to your benefit that if I miss something, and I'll say off the record, even though it's recorded and on Facebook, is part of the problem is that when I started teaching the course, they didn't show me what my final exam was supposed to look like for this class. So I taught the course the way I've been teaching in the U.S., and so some of this I don't necessarily get too wrapped up in. And then since you're going to other schools, they said that the final exam had to cover these things, and they showed me the final exam, so I had to put some questions, rewrite the final exam, to put in some questions that covered material that I didn't cover in the beginning. So I have to go back and pick up those pieces. In my personal opinion, you just saw VHDL. VHDL is the way that 90% of circuits are being designed today, and we don't do this by hand so much. So I skip over a lot of this stuff, but since I'm told that they expect you to have seen it, that I'm going back and putting it in. So I would not there. So my next step is to be, right there, B plus C plus D, right there. A plus B plus D. B naught plus C plus D naught. Now notice that I'm inverting each of these as I do it. A plus B plus C plus D naught. Right there. Right there. So that is my final implementation. So I read the zeros out right there. So now, if I was to draw this, I would draw this with an OR gate with B, C, D. I would draw this one with A, B, D. This one with B naught, C, D naught. And this last one is A naught, B, C, D naught. And that would all go into my AND gate right there. Do the same stuff with the bubbles right there. Right here, right there, and I could go through the discussion. This is actually a NOR gate by definition, right there. So now I've implemented the circuit with using nothing but NOR gates. So the process is, right there, is that we read out the zeros. That tells us what our function is not. We write our function as what is not. We then apply De Morgan's twice to the final result, and we end up with the expressions here. This is what the function is right there. X is equal to this whole thing we read out with the not over it, because we read the zeros, so we have to invert the entire thing. When we invert that, each one of these terms then gets an inversion on it right there. Because if you remember De Morgan's theorem, A, B naught is equal to A naught plus B naught, right? Right there. So we apply that right there. We end up with this expression. Then we turn right around and do it again. Actually, the first one, I was applying A plus B naught is equal to A naught B naught right there. So we apply that one first. So we end up with this term here, and then we apply De Morgan's to each one of these terms. Now, I'll be honest that when I used to teach this all the time in my courses before I started dropping it out of my basic digital course because it's not used very much, I could do that without using De Morgan. I would just know to write the inverse automatically when I read out the zeros. That's there. And I would write it out. I could write it and skip those two steps. I recommend you don't stick to steps because you're not going to do enough of these to really worry about how to skip the steps. That there. You'll probably want to do one or two of these before the final exam when I review for the final. That there. I'll go through this again. But I just wanted to take a little bit of time to go back and highlight the fact that I probably skipped this. That's there. And the reason I skipped it, I don't think it's that important with everything else there is to study. But since the schools you're going to seem to want, still teach it, that I'll put it back. Go back and put it in. That's there. So since it was on the final exam. Any questions? I will try to schedule a lab that's there. I want to do a VHDL lab that's there. And the VHDL lab I want to do is actually going to be a simple counter. And I'm going to have an up-down counter that's there where we push a button, it'll count down, and it goes through the counts. And I want to do it in VHDL just so that you can see how easy it is with VHDL to do counters right there. So that's there. So as soon as I get a chance to get the lab that's there, hopefully I can find a time. I gave up on the lab we were meeting. That's never empty. I found that there's another lab that I can get them to install Quartus on, and we can move the boards to it. So hopefully we can use the other lab next week sometime. With that said, as I said, I've got an appointment off campus at 2:30, so I'm going to. Okay. Oh, that's an hour. I'm getting shorter. I must be burning out there.